So following up on this one, we're going to use F equals MA right here. We have the free body diagram, normal force. mg, this is 8 over 21.54 mg, and this is equal to the normal force, which is 20 over 21.54 mg. So these are both the same. Sum of forces perpendicular to the ramp. Perpendicular to the ramp would equal 0, and those two would both have that value there. That's the free body diagram, equals the mass times acceleration, right? It can only accelerate in that direction. Which do I want to be the positive? Doesn't matter, but once you decide on that, I'm going to say like that, MA, then I'm going to write sum of forces equals MA, and that is my positive direction. Again, this is how I do it. It'll all work out if you do it 6 other ways. As long as you keep track of stuff, I find this the easiest way. So the sum of the forces in that direction is only that component, 8 over 21.54 mg. No other forces in that direction, positive or negative. So that equals MA. And the m's cancel out, and we find out that the acceleration is equal to 8 over 21.5 times 32.2. So 8 divided by 21.54 times 32.2, and we get 11.96. feet per second squared, and it's in that direction there. Then we have that distance of 21.54 feet in that direction. And so we know S and we know A, we need V, right? So I think we're going to go to V final, which would be right here, just before they leave the ramp. Called it V2 on the last problem there. And V initial squared, right here, V initial, plus 2AS or delta S. Now, S is in that direction, and the acceleration's in the other, so that's going to be minus. That's going to equal the 25 miles per hour was 36.7 feet per second squared, and that's going to be minus 11.96 feet per second squared times 21.54 feet. And if you remember, this 11.96 was 8 over 21.54 G. Many times it's just easier to leave it like that in terms of G. I'll show you why. Instead of 11.96, I'll put in 8 over 21.54 G times 21.54. I think it's becoming apparent. Those cancel out. So it's 36.7 squared, 1347 feet squared per second squared minus 2g, not minus 2, minus 16g, but it's not units of g alone. Remember, we multiplied it by feet. It's g, and then we multiplied it by 21.54 feet. So that is also in feet per second squared, g. And we see that we're getting the same thing as before, but using the F equals MA approach, pretty much even on this problem. Again, I want to emphasize that now. These problems aren't very challenging. They're pretty basic. You know, not that they're easy, but they're doable with a little effort. And there's not a huge difference between work and energy, impulse and momentum, and F equals MA for many of the sort of okay problems. But when things get more complicated, F equals MA is going to be disastrous, and work and energy and impulse and momentum, that is what you're going to use. I don't think you'll use sum of forces frequently in junior and senior level mechanical, structural classes, but F equals MA, you probably won't use a whole lot more. You're going to use what is derived from it, and that is work and energy and impulse and momentum. So this one here, so minus 16 times 32.2 equals, there's our 831, square root 28.8, be final 28.8. And then, so I got everything there. You're right back to this here, using projectile motion equations to figure out what you want to figure out, whether it's the time, how long does it take from the end of the ramp. Well, you needed that 28.8 that affects how long it takes between when the person leaves the ramp and hits the water again. One problem you might be figuring out the time, another one the location, another one the maximum height, so on and so forth. I'm pretty sure you get the picture. I will say this, instead of projectile motion, you can use work energy and impulse momentum methods. You'd have to also use conservation approach, and it turns out it's actually a little more lengthy than the projectile motion equations for this here. So we won't demonstrate it, and we haven't even done impulse and momentum yet. So we don't want to get ahead of ourselves. But the equations will work, and you can figure out the time and the position with work and energy and impulse and momentum, but not as easily as you can right here. That's it. Hope you're doing great.